Hi, this is an example problem from Chapter 9 involving the conservation of total angular momentum. Pause for a moment so that you can read the question. So in this problem, we've got a carousel that is rotating counterclockwise. There's no friction here. And there's a person who's initially standing on the side and afterwards grabs onto the carousel. So we've got two situations. We've got an initial situation here where we've got a carousel. Here it is. Here's the x rotation. And it's rotating around with some angular speed, angular velocity, omega I. And that's positive. It's equal to 3.14 rad per second. Again, positive because it's going counterclockwise. And we've got a person here standing along. And since they're not rotating initially, they have got zero initial angular velocity. And I should call this the carousel. Afterwards, that person grabs onto the carousel. So now we've got the carousel rotating, and now the person has jumped onto the edge. And so they're both rotating now with the same angular velocity. So I'm just going to call this omega final, and we don't know what that is, but we're going to try to solve for it. Now, we're also we're going to be able to solve this problem using conservation of angular momentum. So if we remember angular momentum, capital L, it equals the moment of inertia I times the angular velocity, omega. Now, if we have more than one objects that are rotating and only internal torques influence their motion, then the total angular momentum for the system is conserved. That is, we add up all the values of L for each object in the beginning. The sum for those objects will be the same afterwards. Back to our problem. So we know what the initial, in this case, these objects, their moments of inertia aren't going to change. The moment of inertia for the carousel, it's given here. We know what that is. 125 kilograms meters squared. And the person, we're going to need to calculate what it is. So for the person, we can consider that person to be a point mass. Here's the radius from the center of the carousel out to that person, r. And the mass of the person here is m. And so the moment of inertia for a person with point mass m, that's going to be m times r squared. And in this case, we know what the value of r is, right? This is r is equal to 1.5 meters. So this is for the person. Now let's go ahead and use the conservation of angular momentum. So sum of the angular momentum in the beginning is equal to the sum of the angular momentum in the end. Remember, these have to have signs because they are vectors, but everything here is actually going counterclockwise. It's all positive. Now we've got L for the carousel in the beginning, and we've got L for the person in the beginning. Since we have two objects, and the same thing for these in the end, final, person final. Now we do have a zero value here for the person in the beginning, so that means, recalling that angular momentum here is moment of inertia times omega, then for the person in the beginning, that angular momentum is zero because they're not rotating to start with. Now we can write down that same equation. So this is for the carousel, and this is their angular velocity in the beginning. It's going to be equal to I for the carousel times omega for the carousel final plus I for the person times omega for the person final. But in fact, actually, the final is the same for both since they're rotating together, so we can kind of ignore this and just call it WF as we did before. And if we do that, we can go ahead and do a little bit of math here to simplify this equation. Let's factor out omega final. So I'm going to be left with an IC plus an IP for the person, and we factored out that final angular velocity. Finally, we're trying to solve for that value, so let's go ahead and do it. We're going to have to divide both sides. Let me flip the sides of the equation and divide by that term in parentheses there, and then so we're going to end up just with this. And we can go ahead and plug in our values here. IC, which is for the carousel, that's 125 kilograms times meters squared. Initial angular velocity, that is 3.14 rads per second. And in the bottom, we've got, again, for the carousel, the moment of inertia, 125 kilograms squared. For the person, we're going to have to use this formula. That's going to be m, which is, for the person, 40 kilograms. And they are, from the axis of rotation, they are a distance of 1.5 meters away. We need to square that. So that's what's going to go in for IP. 40 kilograms times 1.5 meters squared. And we're going to go ahead and put all those numbers in and see what we get. Move this out of the way for a second. This comes out to 1.83 radians per second. And well, that's our positive final angular velocity, and so that is also the angular speed there. Notice that it's gone down because the person there who was initially not rotating jumped on there and caused it to slow down a little bit.